What I want to do here is just explain how to use the index of refraction. Here's the basic concept, is that the speed of light in a vacuum is 3.00 times 10 to the 8th, okay? Now my geeky calculator, if I ask it what C is, it actually is 299,792,458 meters per second. And I don't think that's changed since this calculator's been programmed, right? So, but what you need to know is that when light travels in anything but a vacuum, it travels slower. Okay, it never travels faster than that, but it always travels slower. So what we've got is something called the index of refraction. And the index of refraction basically is kind of a weird thing. The bigger it is, the slower light travels. So for example, if your index of refraction is 2, then light travels half this fast, right? If the index of refraction is 4, it travels 1/4 that fast, right? So the bigger n is, the slower light travels in your medium, okay? And these are just some indices of refraction. Too many animations here. So a vacuum, of course, it's defined as 1.0, as many zeros as you want to do. Air, most people say that air is 1, but really it's 1.0003, right? Okay, water is 1.33. That's a good one to memorize. And then glass, well, you know, there's not just glass. Glass is not like an element. There's different kinds of glass. Quartz glass, crown glass. These are plastics here. And there's more than that, right? There's lucite, there's diamond. Of course, this is why we'll figure out later. Well, this is why diamonds actually sparkle so much, is it has such a crazy high index of refraction. Okay, so let's do a sample calculation. This is really a pretty simple concept. What's the speed of light in water? Well, if n is the speed of light divided by the velocity, right? Then what I'm going to do is I'm going to say 1.33 equals 3.00 times 10 to the 8th meters per second divided by the speed of light in water, right? Okay, so all I'm going to do here basically is it's going to be the speed of light divided by 1.33, right? And I knew that before I even used the formula, because it has to be less than the speed of light. It's got to be less by that factor. That's what it does, right? So times 10 to the 8th meters per second divided by 1.33. So 3e8 divided by 1.33 on the calculator. Then I get 2.26 roughly. I guess we only have 3 sig figs, so 2.26 times 10 to the 8th meters per second, okay? Okay, now random factoid, okay? Although you cannot go faster than the speed of light, okay? You can go faster than the speed of light in water, which is interesting, because if you can go faster than the speed of sound in air, you make a sonic boom. So if you go faster than the speed of light in water, okay, it's possible to make a kind of a shock wave, a light shock wave. This is called Cherenkov radiation. Okay, so if, let's say, for example, your speed is, you're in water and you go 2.5 times 10 to the 8th meters per second. Well, you can go that fast. An electron can go that fast. It doesn't have to have infinite mass or something like that, right? So it can go that fast, and if it does go that fast in water, it makes a little flash of light. This is called Cherenkov radiation, and this is how we detected neutrinos. The Japanese got this giant underground tank. They put it inside a mountain, and an electron neutrino came in, right, hit an electron and sent that electron off at faster than the speed of light in water, and it made a little flash. And the side of this tank was an enormous tank of water under some mountain in Japan, and it made a little flash, and these little photomultiplier tubes on the side, thousands of them, detected that flash, and we knew we had neutrinos. Yay! Well, okay, we knew they existed before that, but you know, there you have it.